Now let's move on to the time response of a first order system. Now, what do you mean by this first order system? How will you understand a first order system? Suppose you are given with the some transfer function, a closed loop transfer function of the form g of s by 1 plus gs hs. Okay. Now, when you equate this 1 plus gs to 0, you will call this equation as the characteristic equation. Okay, so far we have learned that characteristic equation. When you equate to 0, you will get poles, all these things which we have dealt. Now, as you know that this is going to be a polynomial, right? This 1 plus gs hs, or this 1 plus gs hs is a polynomial, right? It's a polynomial, right? Of the form, it can be of the form s squared plus 3s plus 2, or s plus 1, s cubed plus 4s plus 4s squared plus 3s plus 2s 2. Okay, all these are polynomials, but they differ in their degrees or in their orders. So we will call that this is a polynomial of order 2. This is of the polynomial order 1. This is of the polynomial order 3. Now, when you look at this characteristic equation, you can see various types of polynomials, and polynomials can be of different orders, starting from 1, 2, 3, and it goes on like that. Now, when the characteristic equation of a particular system is having an order 1, then we call such a system as the first order system. Okay, this is to be made very clear before going into find out the time response. Now, next question is, from where will you find out the time response? So we will start with the basic first order system transfer function. Okay, assume that you have got a transfer function which is given by 1 by st plus 1, right? So this is a transfer function, and this you can write this as okay, so this is 1 plus, so this is actually what? This is actually c of s by r of s. So this is a transfer function. So if you, okay, just represent it as a single block, you can write like this. This is your c of s, this one is your r of s, and this block will be having 1 by st plus 1. But this is not the real block diagram. We are going to deduce the block diagram anyway. But anyway, so first of all, what you need to find out is, so this is a transfer function. Now, when you equate this characteristic polynomial, this is a characteristic polynomial. This is of the form st plus 1, or the order of this polynomial is equal to 1. That's why we call this transfer function as the transfer function of a first order system. Now, I'm going to introduce one more term called as t, which is called as the time constant, right? So t is what is called as a time constant, and based on this time constant, now we know that you have studied in your electrical circuits, the time constant is actually depending on the components, like you have RC, LC, all these relates to some way or other, it relates to time. So this is, as long as resistance and capacitance remains a constant, that the parameter is going to be constant. That's why we call this is some way or other it's related to time. And as long as these components are constant, you are not varying that time to time, you are not varying the resistance and capacitance. Once it is designed, it is designed. That means it is designed for a particular time constant. So the value of that time, so the transfer function depends on the parameter called as time constant, and we will be dictating the time response in terms of this time constant, which you will find a short while from now. Okay, now let's try to draw the block diagram from this transfer function. Now, how to draw the block diagram of this? So some way or other, we know that this c of s to g of s is also equal to, generally it is called as gs plus 1 plus gs hs. Okay, so you need to convert this into this form. Now you have only 1 by 1 plus st, and that is in no way it is comparable with this. So you can make this comparable by doing some manipulation on this transfer function. Now what if I'm taking est outside from this? So when you take st, you will get this as st into 1 plus 1 by st, or you can call this as 1 by st. You can bring this to the numerator, and you can call this as 1 by 1 by st, right? Now I am just putting this as into 1. Okay, no problem in that. Now I'm again going to write this GFS by 1 plus GSHS, right? So this is actually a transfer function of a negative feedback closed loop system. That we know. So in comparison, now just compare. So what you will get, your g of s is going to be 1 by st, and here also you have a g of s into 1. That means you have an h of s is equal to 1. Now if you know g of s and h of s, you can, and not only that, this plus shows that this is a negative feedback system. You can simply draw the block diagram, right? So the forward path gain will be 1 by st, right? And this is your c of s. Now from the c of s, you are actually giving a feedback, say something like this. This is minus, this one is r of s. So what is this value? This is going to be 1, right? Right? So this is actually 1, and it is a negative feedback because this is 1 plus GSHS. So from this you can convert this into the block diagram. So this is actually a block diagram of what? Of a first order system whose transfer function is given by 1 by st plus 1. So it's not, it is so it is not an open loop system. You can consider this as a closed loop system, and that too an unity feedback control system. Okay, now we are going to study the time response of the first order system. Now in order to find out the response, actually what's the meaning of time response? Time response meaning is to find out c of t. Now if you want to find out c of t, you need to give r of t, which is your input, right? With the input only you can measure the output. So r of t. Now what are the r of t's that you are going to give? Now we have already studied in our introductory classes, or in the second or third video, I think, we have studied something about the test inputs. Why they are called as test inputs? Because those inputs are used for testing the output. So the important test inputs that we studied are, will be okay, the important inputs that we studied are, we started with the step input, then you have went on to ramp input. Okay, in this case we are not considering parabolic input, and another important input is the impulse input. So these are the three test signals that you are going to apply to this particular system to find each response. So when you give the step input, you will call the C of t resulted due to that. Due to this R of t, we will call as the step response. When you give the ramp input, we will call that as a ramp response. And when you give the impulse as the input to that system, you will call that as a impulse response. Now to start with, let's start with to find the step response. Okay, so the step response. Now, what do you mean by step response? As I told you, say in a time domain system, in a system, when you give your r of t as the step input, so you are considering that as a unit step. Now, when you give u of t as the input, say for example, consider the block as this. So you are going to give an r of t, which is u of t. The response you will be calling as the step response. Now, we know that your C of S by R of S of this system, we are going to find out the step response of the system. Now, C of s to R of s is what? It is given by 1 by st plus 1, right? Now, from this, you'll be able to get C of s to be equal to R of s into 1 by st plus 1, right? Now, we know that what is R of t? R of t is R of u of t, right? So, how will you find out R of s? It is the Laplace transform of u of t, which is 1 by s, right? So, this will be 1 by s into st plus 1, or so your C of s is equal to 1 by s into st plus 1. So this can be written as a by s plus b by st plus 1. Okay, now you know how to resolve this out. You know how to do this partial fraction. You may do it by yourself. So you will be getting a to be 1, so you can put a to be 1 by s and b to be minus t. Okay, so you may just find out. So you'll be getting this like this, 1 by t by st plus 1. Or now to convert this into a standard form, you can say take this t outside, so that this becomes s plus 1 by t, and this t and t gets cancelled. So you can write this as, so when you can find out C of t, so this is your C of s. Taking the inverse, you will get is as 1 by s as u of t, or you can put that as 1 in the time domain, 1 minus e raised to minus t by capital T. Okay, 1 by s plus 1 by t. You may just recollect, or you may just refer my signals and systems note. So there you can find out 1 by the inverse of 1 by s plus 1 by t to be e raised to minus t by t. Okay, so this is your C of t. Now, or in a sense, you can call this as the step response. This is called as the step response, or the time domain response for the step input, right? Now what you will find is, now you want to analyze this. So for to analyze this, you need to plot this graph, so you can find out values at t is equal to 0. What is at t is equal to 0? C of t. When you put t is equal to 0, this becomes 1, C of t becomes 0, right? When you put this will become 1 minus 1 0. Now what about C of t at t is equal to infinity? T is equal to infinity, meaning this becomes 0, or this becomes equal to 1. So you can come to a conclusion that, so you can draw the graph as, so it starts with 0, right? And okay, so it will be reaching its highest value 1 only at t is equal to infinity. So you need to find out some other values in between. So how will you find out that value? Now that's what I told you, that now the time response will be dictated by a parameter called as a time constant, where t is the time constant. Now you can put some multiples of t, capital T, right? So you can find out C of t at t is equal to capital T, meaning this is one time constant. One time constant. What happens at one time constant? So time constant can be anywhere over here. So I'm just marking this time axis as 1t, 2t. Anyway, these are all time. So you can represent that as 3t, 4t, and so on, right? Now what happens at C of t at t is equal to capital T? Now when I'm putting C of t at capital T, what I'm going to get is 1 minus e raised to t capital T by t, right? Or this is going to be 1 minus e raised to minus 1. Now this you can find out from the calculator. Okay, so you will get this as, 0.632. Now similarly, you can find out C of t at t is equal to 2t, C of t at t is equal to 3t. So what you need to do is substitute this t. So I'll just do this for you again. E raised to minus 2t by t. This t and t gets cancelled. So this becomes equal to 1 minus e raised to minus t. And similarly, you will be getting this as 1 minus e raised to minus 3. And you can find out from the calculator the answers. So the answers are going to be Okay, now look at this. So you have C of t at t is equal to 2t, you will be getting 0.86. Then C of t at t is equal to 3t, you will be getting 0.95. And C of t at t is equal to 40, you will get a to be 0.98. So what's the meaning of this? So as t increases, so we found out the two extreme times, right? At t is equal to 0, it is equal to 0. At t is equal to infinity, it is equal to 1. So all the other values comes in between the 0 and 1, but we see that as at t is equal to 40 itself, what happens? This approaches to almost equal to 1. So, but it will be only at equal to 1 only at t is equal to infinity. Ideally, that's right. But practically, it's not possible to wait for such a long time. Now, you cannot. That is an ideal time to wait for the system to be at 1. So, let's try to draw this plot. Now, what happens at t is equal to t? T is equal to t means it is 0.63, means it's greater than 0.5. So this may be, so okay, this will be 0.5. Okay, let us call this as 0.63. Okay, I'm marking here. Now at 2t, what happens is it is 0.86. So that becomes a bit more higher. Okay, now at 3t it becomes 0.95 and it becomes closer and closer. So joining these two lines, you will get this as what? You can join these lines. Okay, so you're going to get a graph like this, but it will reach at 1 at infinity. Okay, so now what's the point? Now, ideally speaking, this will reach only its steady state. This is called as a steady state, and this the time that is in between is called as a transient state, ideally speaking. So that is a steady state. So the steady state, it will reach only at t is equal to infinity, but practically you cannot consider that as a steady state. You need to consider some other points beyond that time. Okay, now here comes the another term of called as tolerance. What do you mean by tolerance? The allowable error. Okay, now if you can accommodate, or if you can bear a 5% tolerance, then your 3t, at 3t, the answer is going to be 0.95, or you can consider there is no problem for you if you have a tolerance of 5%, right? 5% tolerance means it is the allowable error. That means you can consider this as 1, right? Now, that's a practical case. Or here, if you want the tolerance to be 2%, you can consider this t is equal to 40 as the time it reaches the steady state, right? So this is so practically speaking, this can be the time it reaches the steady state, or this can be the time that it reaches the steady state, but that depends on the tolerance that you provide. Now based on that, you can define one more term called as TS, which is called as a settling time. Now what do you mean by settling time? Settling time, you might have understood what is settling time by right now. That is, it is the time taken by the system to reach the steady state as it progresses through the transient state. So as I told you, the response actually consists of two parts. One is the transient response, the other one is a steady state response. So practically, this will reach its steady state either at t is equal to 3t or 4t or at 5t. It depends on the tolerance that you provide. So if you assume the tolerance to be 5%, you can call this t is equal to 3t as the settling time. And if you provide a tolerance of 2%, you can call t is equal to 40 as the settling time. Okay, now that's it. So okay, so that's it. So your TS can be 3t or TS can be equal to 40. So I hope you understood this. So practically speaking, this is the tolerance time. This is the steady state, or this settling time acts as the demarcation point. So okay, so this can be a TS, where the system provides a 5% tolerance, or this can also be a TS where the designer provides, so it depends on the designer, so, or it depends on the application. So for some critical systems, the designer will be wanting less tolerance, so that means they will be giving you only 2% tolerance. 2% is a error. Now let us see what is the error of this. So you have got C of t, right? Now what will be the error? So this is C of t, that is 1 minus e raised to minus t by t, right? Right? Now coming to this block diagram. Now from where will you get the error signal? Now this actually, okay, this one is actually the error signal, right? This one is the error signal. Say you can call this as E of t or E of s. Now in this figure, you will be getting this as R of s. What is this? This is actually R of s minus C of s, right? Now what we are going to do is the same thing. We are going to find out the error due to that. Okay, so what is that? So that will be, so look at this. So R of t minus C. So in this case, so this is actually R of s minus C of s, or in time domain you can call this as R of t minus C of t, right? Right? If that is the case, what will you how will you define this E of t? From the block diagram, we understood it as R of s minus C of s. That is your E of s, right? That's your E of s. So from this you can evaluate your time domain, or you can convert this into time domain. That is R of t minus C of t. Now what is your R of t? R of t is 1, right? Because the R of t you have given as the unit step. So this is 1. 1 minus, what about this? 1 minus e raised to minus t by t, or you are going to get this as e raised to minus t by t. Now let us plot the error signal versus time. Now the same thing, when you plot this E of t versus t, this is actually C of t versus t, while this is E of t versus t. That is, you are going to find out the error. Now what happens at C of t, E of t at t is equal to 0? Putting t is equal to 0, you will be getting this as 1. So the error is maximum at t is equal to 0, right? At t is equal to 0. So that's what this figure shows. So when a step input is given to the system, what we expect was, at the very moment at t is equal to 0, you are expecting a 1, but you are not getting in the real time. So that means at t is equal to 0, the error is maximum. This much is the error. So this is shortage by 1 unit. Now, what happens at E of t at t is equal to infinity? Now, when you put t is equal to infinity, your error becomes 0. That means, so at t is equal to 0, it reaches the steady state ideally, right? So at that point, the error between the input and the output is 0. That's what it shows. Now you can just put t is equal to 2t, 3t, 4t, and you can see that difference over here, right? So you can see as a t is equal to t, 2t, 3t, what you can find is that t increases, the error keeps on decreasing, right? The error keeps on decreasing, and it reaches at a point at t is equal to infinity, that's going to be equal to 0. Now, in a practical case, you will assume that at 3t, if it provides a 5% tolerance, you will assume that the error is, or you will ignore the error if you can provide a 5% tolerance, and at 40, if you can provide a 2% tolerance, you can just ignore the error, or you will assume the error to be 0. But ideally speaking, this will be error free only at t is equal to infinity. Even though that's ideal case, for a practical system, you can consider this 3t, or at 40, the error is so minimized, it will be less than or equal to less than 5% of error. So if that is tolerable, then you can consider the time from 3t onwards, you can consider that to be the error. So what we call this error as, this error is called as the steady state error. Okay, steady state error, that is, we are actually calculating time instant, we are calculating what, calculating the error at each point. Okay, now at the time t is equal to 0, at the start of the time, the steady state, in comparison to the steady state, the the error is maximum, right? Now, as time increases, what happens? As time increases, it is approaching to its steady state, and it's coming, the response is coming closer and closer to the steady state. That means the error decreases. That is for the unit step response. Now, in the next session, we'll see what is its impact on the ramp response. Okay. And the next section, we are going to see what is its effect on the ramp input. Okay, now let's see the ramp response of a first order system. Okay, now what is the meaning of ramp response? You are giving, you have a system, and you are again considering a system with the graph, with the transfer function 1 by st plus 1. Okay, so you're again considering the same system 1 by st plus 1, that's a first order system, but instead of u of t, you are giving r of t as the input, and you are going to evaluate the c of s, right? R of t, or I mean the ramp. Okay, don't get confused with that r of t which we have represented for the closed loop system. So this is a ramp input, and the response is going to be the called as a ramp response. Now let's see what is it. So this is a z of s by r of s is actually your 1 by st plus 1, right? Now what is your r of s? See, r of t is actually t, right? That's your ramp input. Now what is your r of s then? When you take the Laplace transform, you will get this as 1 by s square, or c of s is equal to 1 by s square into 1 by st plus 1, right? Now you may just evaluate this as, you can do it like this, a by s plus b by s square, right? This is how you do this, by c by st plus 1. Now you may just, the work is given for you, you may just do it. So you will get your c of t as what? You're going to get your c of t as t minus capital T plus t into e raised to minus t by t, right? This is how you're going to get, right? Now this is your c of t. Now once when you try to draw this, okay, try to draw this graph, what is actually you're expecting? The ideal thing that you're expecting is this, right? Okay, you're giving a ramp input, so the ramp is the control input that you give, and the output you are expecting to be a ramp. Now let's see what is there any, is there anything wavered from our expectation? Now what happens at t is equal to 0? At t is equal to 0, you can find out your c of t to be what? Minus, at t is equal to 0, what happens to this? This becomes 1, so this is minus t plus t, this is t is equal to 0, which is equal to 0. So it starts from, well, it starts like the ideal RAM input. Now what happens at t is equal to infinity? That's what we are going to find. C of t at t is equal to infinity. So putting t is equal to infinity, this becomes 0, right? E raised to minus infinity is 0. So that means you're going to get this as t minus, sorry, this is actually infinity minus t, so this is going to be infinity, right? So what does this suggest? So, right, so at t is equal to infinity, you're going to get a graph like this. So anyway, yeah, obviously the ramp has to be infinity, So you won't be getting an idea. So you may feel that it will trace in this way and it reaches infinity. See, because c of t at t is equal to infinity is showing you infinity, you may be thinking that this will be going in this line. So will there be any change? For that, what you need to know is some other points other than t is equal to 0 and t is equal to infinity. We have already defined that that's to be in time constant, say putting t is equal to capital T. Now what is that? Now at what is c of t at t is equal to capital T? Putting small t as t, t minus t plus t into e raised to minus t by t, right? So this becomes 0. So what you're going to get is e raised to t into e raised to minus t into e raised to minus 1, right? T into e raised to minus 1, or you will be getting this as t into e raised to minus 1, or t into 0.36, right? T into 0.36 t, right? So at t is equal to t, right? At t is equal to 1t, you are getting this to be 0.36t, right? So at t is equal to t, what must be your r of t? R of t at t is equal to t is capital T. So you need to get an expected value is this t, right? So this must be your capital T. Then only you can call this as a ramp. But what is the value of that? At t is equal to t, this is 0.36, well below this value, 0.36. And as you go further, you can see that there is always always an error coming in this way. This is not the ideal, right? Now, from this, we are going to find out the steady state error. Now, know we have found out E of t to be what? E of t is nothing but it is R of t minus, that is the input minus the output. So that's what you get from this block diagram, right? So from the block diagram, error signal is R of t minus t. So this is equal to t minus t plus t plus t into this minus t into e raised to minus t by t, right? So what you get is this t and t gets cancelled, and what happens? So this will be t minus t into e raised to minus t by t, right? Now what is the error signal? This is actually the steady state error, right? Now this e of t at t is equal to 0 is what? At t is equal to 0, the error is 0, right? That's what we understood. At t is equal to 0, both the ramp and this response is the same. That is, at t is equal to 0, the error is 0. Now what happens at e of t at t is equal to infinity? When you put t is equal to infinity, this becomes 0. That means your error is t, right? So as it approaches t, this gap increases and it will be having an error equal to time constant, right? The error equal to time constant, right? So the steady state error for a ramp input, there is an error for a ramp input, but what we have seen in the case of a step input, we have seen that the steady state error is 0. That's what I told you, that the system not only depends on the transfer function, that also depends on the input that you give. Say for a first order system, as we have seen, the it depends on the input as well. For a step input, the error is 0, but for a ramp input, there is a error equal to its time constant at its steady state. Now, let us see the two responses, the impact of varying capital T. That is, as I told you, this is a time constant, and time constant is something which depends on the internal components. Now, varying the components, you can increase or decrease the time constant. Now, what happens if you decrease the time constant? This t, if it is decreased, you will be getting a graph like this. That means as your time constant decreases, you can make the response faster in the case of the first case. Now what about the ramp response? Now as you decrease the time constant, you can reduce what? Reduce the steady state error, right? So but we'll see that in the coming sessions that reducing too much of time constant and increasing too much of time constant has its own limitation, and we need to be very careful in dealing with those things. So anyway, these are the two responses that we studied: the unit step response and the ramp response. In a step response, there is no problem even, and the steady state error is 0, while in the ramp response, we found out the error remains equal to the time constant. Now, the only solution to reduce the error is select the components in such a way that the time constant becomes so minimum, so as to minimize the error if you want to give a ramp input to a first order system. Okay. Now coming to the impulse response, and I'm going a bit fast right now. So this is C of S by R of S is equal to 1 by ST plus 1. So your R of T is your, since it is impulse response, it is del of T. What is your R of S? R of S is equal to 1. So substituting R of S to be 1, you will get this as 1 by ST plus 1, or you can st plus 1, you can take this t outside, or this will be 1 by t into s plus 1 by t. Okay, so this will be 1 by t e raised to minus t by t. So when you try to draw the graph, so this is actually your okay, sorry, so this will be your c of t, that is the inverse of this. So when you take the inverse, you will get this as c of t. Marking the c of t at t is equal to 0, what happens? At t is equal to 0, this is 1, right? So that means this is having a maximum amplitude of minus 1 by t. And what happens at t is equal to infinity? That reduces to 0. So that means you'll get a graph like this. So what you're expecting is the impulse is usually represented by this, right? When you give an impulse to this first order system, what you expect is an output like this. But it will be going a maximum of, it shows that the response goes a maximum of 1 by, or the reciprocal of the time constant, and finally it reaches to 0. So it almost follows a practical impulse signal, even though ideally an impulse signal is drawn like this. I have told you while I've took the signals and system course, that is it practically an impulse signal reduces like this. So that means it has a close proximity to the impulse, practical impulse signal. Okay, fine. Hope you understood this, the responses. I'm just again have a briefing on this. So we have found out the C of t, the step response. Here is it. The step response is 1. The step response for a first order system is 1 minus e raised to minus t by t, and we have found out the error to be, the steady state error to be e raised to minus t by t, and we have seen that as steady state error becomes equal to 0. Okay, so this is the equation for error, and the steady state error is actually e of t at t is equal to infinity. This is what is called as a steady state error. That's for the ideal case. And practical case, you can take this 3t and 4t, you can approximate to be almost equal to 0. Now coming to the ramp response, this is your ramp response, and we have found out the error is this thing, and the steady state error we found out, this is actually your, so you may just change, I have told you that this is the steady state, this is just the error. The steady state error is the error at, ideally speaking, error at t is equal to infinity. So this is e of t at t is equal to infinity, and you found out that that remains equal to the time constant. And finally, for the impulse response is given by this 1 by t e raised to minus t by t, and we have seen that it closely approximates the practical impulse signal. Okay.